Okay, good. That should be going again. Anybody still need those? Don't worry. If you try it by next week, it'll be okay, right? And a lot of times, maybe that we can make that decision tomorrow when I see if I forgot anything. We can decide, should I update the equation sheet with some simpler, handlier stuff? Like the a equals v squared over r is not really in there. It's f equals ma equals mv squared over r. Cool, okay. You should really check this. Okay. Big G is 6.67. See if Newton had his head on straight, because there's an argument he's pretty crazy. 5.97 times 10 to the 24th kilograms divided by 6.37 million meters. Don't forget to square that denominator. What does that come out to? Okay. And instead of 36 million meters, what if we're only 300,000 meters? That's just high enough to be like outside the atmosphere. That's where the space shuttle goes to work on other satellites. So if we need a geosynchronous satellite, like in the previous example, we have to put it way up there so it can fall towards Earth with the right acceleration, and we put it going sideways so that it keeps track, it makes it around in 24 hours. Geosynchronous orbits with the planet Earth will only actually exist at that altitude. 36 million meters out or so. Okay, what if we're only 30,000 though? This is really close. Domes. Ugh. Did you plug in those numbers yet? This would be like 0.3 times 10 to the 6th. So it would be almost the same. Okay. If you crunch those numbers, you should get 9.81 with units on its meters per second squared. Okay. If you only increase, that's a test question I love to give, especially like if it wasn't Earth, if it was the moon, we could orbit the moon like 1,000 meters or whatever you need for the above the highest mountain. So maybe like 5,000 or 10,000. You could orbit the moon just above the surface and there's no air. Right? If I add whatever this is, zero point 0.3 or zero point 0.03 to that number, it doesn't really change it at all. Right? In fact, that's why we only keep so many sig figs, because if we're adding and subtracting to that number, we don't even need the other digits. It doesn't matter if we add or subtract something small. Okay. So what velocity is required for the shuttle to orbit just above, and what time? I kind of will help you do this. So now our radius of this orbit, 3,000. Instead of 6.37, I think we've got 6.67 million meters. I don't know how much time that's going to take. Okay. What can I do? Well, I could believe that it's g. I could say g equals my centripetal acceleration there, v squared over r. Okay, if I didn't believe in g, I'm going to try it with g, but I would have to do gm over r squared. So my new r for this problem is 6.67. It's eerily similar to the gravity constant digits. Let's see. I do know the radius, and I know how to make circles. So what I'm really after is, I want to use this formula again. I would like to take 2 pi r divided by the time to go once around. Time is what I'm looking for. Sorry. Yeah, I think I need, because I can't think of any other way to do it. I know 2 pi r and I know r. I don't know how fast it's going. Okay? Like I could do, no, no, no. That's right. I think we're going to end up at number 2. Okay? Oh, yeah. Wait, wait, wait. Mass of the Earth, gravitational constant, those are just constants? They're 9.8? Couldn't I just solve this? Little v equals, if I believe in little g at that altitude, it's probably a little different. Or I could just do big G, big M over R. Yeah. Yeah, you can just do that. That's right. If you don't want to use 9.8, you can just plug it in and solve it. Exactly. Okay. Am I prepared enough to just write down the answer? I think I worked it out. Yeah. Did you get 7726 meters per second? Isn't that like 18,000 miles per hour? I think it is. And if you go around that orbit, okay, so the time is just 2 pi r divided by this v. And 2 pi r is really huge because r is millions of meters. You get this weird number of 5,424 seconds. But if you convert carefully, that's actually about 90 minutes. You did not get that. Oh, you use little g. If I take 9.81 times my fancy new radius, and then take the square root, oh, I get about 8,000. It's a little too big. We're already too high. Okay, we better plug in. We better do big G. That's on the equation sheet anyway. V equals gm over r. If you're in an orbit, at any radius, you can skip to the speed by taking g times the mass you're orbiting around and divide by r. Okay. Let's see. People on the space station have big issues sometimes because you're so low and you're going so fast that you can tell that you're zipping around the Earth. And you, of course, only 90 minutes pass and you zip over it, so people get dizzy. You can tell that you're falling, is what they say. You're so close, you can actually tell that you're going down and down and down, and you're just missing it. And they go all the way around the Earth every 90 minutes. Okay. Hopefully you can see from these examples that the closer you are into Earth, the smaller this radius, the faster you have to go to stay in orbit due to gravity. Okay, so you have to move out until you're at a 24-hour orbit.
So why did you change the radius from 6.67?
It was 6.63 because at 6.63 we're right here at the surface, and there's air everywhere and buildings and trees and stuff. And actually, if you try to smash through the air at that speed, you explode and burn. You can't go through. We're working now, when you hear hypersonic aircraft, they're working on stuff that can actually cut through the air, even though it's going so fast, it like turns the air to plasma when it hits the air. The air literally turns to fire because of the pressure of this thing moving through it. So when you say like a hypersonic aircraft or a hypersonic weapon, that's what they mean. They don't mean supersonic, like airplanes can fly through the air at Mach 10 or whatever. That's just supersonic. When they say hypersonic, they're not even flying through the air. They're turning into plasma, and they're like burning their way, like when a meteorite comes through and it leaves this huge smoking trail, right? Because it's just burning its way through the air. Yep. We kind of crash. Okay. Well, that's been enough time out of me. Tomorrow, the notes I forget or don't get to is Kepler's laws. There's some silly old laws that Kepler noticed with the planets. They actually, one of Newton's claim to fame was he could explain Kepler's laws that are older than Newton's laws. He could explain, excuse me, he could explain Kepler's laws with his own law of gravity. Okay, but this was enough examples. You can see that you can just plug in gravity for that centripetal force for mv squared over r. You can set them equal whenever something's orbiting due to gravity, and you can just start solving stuff. This v equals 2 pi r over t is very handy going around a circle. Or you can rearrange for whatever you want, right? If I gave you velocity and time, you could find the radius. Okay? Any questions? Okay. That's plenty. Oh, pause that.